In number 1, we are given that we have the graph of the position function. Do keep in mind that's what S at t is representing. And so here is our position function, S at t, and we want to know which of the following is the graph of the velocity, V at t. So again, if we go back to PVA, and we are at position, and we need to get to velocity as we move down this chain of events, you're finding the derivative, which can also be the slopes that are going on. So notice that is this function here, no matter where I'm at on the function, S at t is decreasing. And so if S at t is decreasing everywhere, if the position is decreasing, then we automatically know that V at t, or the velocity, is less than 0 everywhere. So that tells me that the graph of this has to be completely below the x-axis for all values of x. And so that's going to give me answer choice D. Okay, our next question. We are given a velocity graph, and we are asked at what time does the particle reach its maximum speed. Now, we do need to remember that speed is the absolute value of velocity. And so to take a velocity graph and make it into a speed graph, then we're going to flip all these points over. So at 2, -2 is actually going to become 2, +2. 3 is going to become +2. 4, here's somewhere between -2 and -3, so somewhere up here between the +2 and 3. 5 is going to flip over and become +3. And so notice that really with this graph, we end up with something that looks like this for our speed graph. And very quickly from that, we can see that the maximum value that speed obtains is right there at 5, and that's what it's asking us is at what time. So at time t equals 5. Our next question, we are given the graph of velocity, and we want to know how many times does the particle change directions. So we know that when velocity is greater than 0, my particle's moving to the right. And I drew a left, go me. I'm moving to the right. But when velocity is negative, then my particle's moving left. And so since we have the graph of velocity, that's going to translate from above the graph to below the graph. So how many times does my graph change from above to below? And that's going to be right here at 3, and it only changes once. So answer choice A. And for our next problem, again, we have the graph of velocity. And we're asked over what interval is the particle slowing down. And so again, we have 2 options here to look for. One is we can make a velocity or a speed graph. Notice you're talking about slowing down. So we're talking about speed there. And we know that a particle slows down when our velocity and acceleration have different signs. So one's positive, one's negative, and it doesn't matter which one. Now, graphically, what that translates to is if I'm given the graph of velocity, which I am, you're going to be looking for either above the x-axis, so above and decreasing, or you're looking for below and increasing. Because if you're decreasing here, then you know your slope is negative, which is your acceleration. So if we think about those 2 things, then if we are above the x-axis and decreasing, that's going to happen right here. And then if we look anywhere else, then we will need to have below and increasing, which I don't have below and increasing. So the only interval where I am above and decreasing would be E from 2 to 3. Now the other option would be to take all this negative parts and flip those over, and that would give you the graph of speed. and that would generate the same answer. So for number 5, according to the graph shown, for how many times from 0 to 8 is acceleration not defined? So again, let's figure out where we're at in our chain of events. We're given the velocity graph, so I'm asked about acceleration, so I'm moving downward. So I'm looking for the derivative, and it says not defined. So I know a derivative is not defined at sharp points, and that's because the slopes from the left are not equaling the slopes from the right. And so looking at our graph, we see that we have a couple of places where we're not going to have v prime or the acceleration defined. One sharp point would be up here and down here. Now this graph does continue here. And again, if you want to examine the slopes that I was talking about, as your graph is decreasing, those slopes are negative, but then notice very abruptly I changed from decreasing to constant, and that means those slopes are 0. So notice at that meeting point, we don't know if it was negative or if it was 0, so we're going to say at those sharp points it does not exist. So notice again, and up here, we're increasing, so those slopes are positive, but very sharply we turn to decreasing or negative slopes. So we have 2 places where acceleration would not be defined. Okay, for number 6, we are asked about average acceleration. And so here, if we're asked for the average value, we have to go back and look at the previous function. So if we want average acceleration, that's really talking about AROC, average rate of change, not at that precise moment what's going on, but over a longer period of time. So for AROC, that's going to be your slopes, and so we need to find our ordered pairs. We have 2 something and 5 something, and we're going to get those from the graph. So at 2 we have a positive 2, and at 5 it looks like we have a negative 4. So now we're ready to do our slope formula. Now the way we need to write this out is going to be your average rate of change. Is really these values are from velocity. That's all we really have here. So we're going to say we have v at 5 minus v at 2 all over 5 minus 2. That's how we're going to be getting our values. And v at 5 is negative 4 minus 2 over 3. So it looks like here we're going to get negative 6 over 3, which is negative 2. All right, so number 7, when does the particle in the graph shown first reach its maximum speed? So here again we're looking over a closed interval. The first place that we reach our maximum speed, which is the absolute value of velocity, again that's going to occur here at 5 because we are imagining this graph flipped over. So the answer for number 7 should be E. Okay, for this problem we're asked about when is the particle's position farthest to the left. Keep in mind you're given a velocity function. So how do I know the particle's moving left with velocity? Well, I know that if velocity is less than 0, the particle is moving left. If velocity is greater than 0, then we're moving right. So I'm looking at the graph trying to find where all of the places where velocity would be negative, which is below the x-axis. So from A all the way to C, that entire area there, all of that is negative. So velocity is less than 0. So my particle starts here at A and we're going left, going left, going left, and he continues or she continues moving left until we get to C. So my answer choice here, it should be C. And number 9, according to the graph, for what time t does the particle reach its maximum speed? Well, again, that would be taking all of this here, and we're going to flip that over to be 3 places up here. And again, if we go through and graph that, we would see that the maximum speed there is going to be reached at B. Okay, so for number 10, according to the graph shown, for what times t is the particle speeding up? And again, if you're talking about a particle speeding up, then you're talking about velocity and acceleration having different signs. And so again, if you're given the velocity graph, which you are, then you're going to be looking where you are above and decreasing, or you are below and increasing, because then we know that velocity is positive, acceleration is negative, or the other way around, velocity is negative and acceleration is positive. So looking at our graph, we need to be above and decreasing, and so above and decreasing, well, that's going to happen through here from D to E, and below and increasing is going to happen from B to C. So again, let's see if we can find our answer choices. We've got D to E, and then we've got, I'm answering it number 11, sorry, I was looking for speed decreasing. So that one, let's see, because I was looking at 10, did not have the answer. So B to C, and then we've got B to C, and then we've got D to E. So answer choice A. Okay, now where is the particle speeding up? Speeding up means that we have the same signs. So that means that we're going to be above and increasing, or we're going to be below and decreasing. And again, please keep in mind this is because we are given the graph of velocity. That's why we can say this. If that graph changes, then certain things have to change. And then we would have to bring in concavity to get our acceleration. All right, so let's see. Where would we be below and decreasing? Well, that's A to B. And above and increasing is C to D. So we're going to have A to B and then C to D, which is answer choice E. Okay, so for our next two, notice that this, according to the graph shown, again, it's talking about the speed of the particle, and it's talking about moving left or right. And so for number 12, answer choice B is the correct one, because again, the particle is moving left with a decreasing speed. So that's going to be the right way to describe what's going on in our graph. And then using the information shown in the graph, at what time t does the particle reverse direction? So where does it change directions? It has to change at C. Okay, with number 14, we've got a nice piecewise linear function. So that tells me I can find slopes and all kinds of stuff. We want to find the acceleration of Karen's bicycle at time t equals 7.5. Now keep in mind we're given the graph of velocity and we're asked to find acceleration. So again, let's go back to PVA. We're at a velocity and we're trying to get to acceleration, so that means we need the derivatives, which means we're probably looking for a slope. So really in our notation for this, since these are free response, let's be careful with their notation. We are finding A at 7.5, and notice that we are approximating it because we don't have a for sure graph of acceleration here. So 7.5 is somewhere between here 7 and 8. So we're looking for the slope of that line segment right here. So let's look at our ordered pairs. Okay, so for our ordered pairs for here, we have 7, 0.3, and then our other ordered pair that we have is 8 and 0.2. So we're just going to do our slope formula here. So changing y's, remember it's changing y's over changing x's. So we're going to say 2 minus 0.2 minus 0.3 over 8 minus 7. And notice that's going to give us negative 0.1 over 1. You're welcome to stop there. Do make sure that makes sense. Does it make sense that we got a negative acceleration? Well, yeah, velocity's decreasing there. Now we need to indicate our units of measure. So remember, velocity, we were told, is measured in miles per minute. So we're going to have miles per minute. That's the top part. Those are those velocity over per minute, or you can do miles per minute squared. All right, so now for part C. Shortly after leaving home, Karen realizes she left her calculus homework at home. What a great kid. She turns around and goes and gets it. I'm so proud of Karen. At what time does she turn around and go back home? So we know we are changing directions, and we're going to change directions here at time t equals 2. So you're going to say at time t equals 2 minutes, Karen turns around, but you've got to give a reason for your answer, and you probably can't get credit unless you justify this. So at time t equals 2, we can say that v at t changes signs. And that should get it. That anything of that, I wouldn't put too much more because math people don't want to read. So here, v at t changes signs should be plenty of information. Okay, for our next free response question, it tells us that a car is traveling on a straight road with velocity 55 feet per second at time t equals 0. From 0 to 18 seconds, the car's acceleration in feet per second squared is the piecewise linear function defined by the graph above. So notice that we have the acceleration function given to us. So think about, we're at PVA. We're all the way down here. So if we're going to track back up, we're going to have to find some area to get to whatever we're asked. Now, it depends on the question, though. So let's go ahead. We know all of this from just what we're given. And part A says, is the velocity of the car increasing at time t equals 2 seconds? Why or why not? So we know that v at t is increasing when a at t is positive. We know that to be true. So if I knew what a at t was, I'd have a good understanding of what's going on here. So let's see, a at 2 equals, and since we're given the graph of it, we can just look right up here and see. A at 2 is 15, and 15 is greater than 0. So what we can say is v at t is increasing because a at 2 is positive. That gets you full credit. So knowing these rules sure do help. Okay, our next question. We are asked, let's see, for each of v prime at 4 and v prime. So we've got to find those values or explain why it does not exist and indicate the units of measure. So very quickly, I go back up and I notice that we are given the graph of velocity. And to find v prime at 4, then we have to find slope. That's what these are asking for. That's a slope or a derivative. Now, v prime at 4, please don't tell me that it is 20. It's talking about the derivative value right here. Already, I see a sharp point there. And so, to find that derivative value, notice that the slope values from the left are not equaling the slope values from the right. They're not going to equal each other. So, I'm not going to have a derivative value there. So I'm going to say v prime at 4 does not exist, and we need to say why. And so we're going to say, or does it ask us to explain why? Yep, explain why it does not exist. Does not exist because And instead of saying a sharp point there, let's tell us what about that sharp point makes us not differentiable there. And it's going to be because the slopes from the left does not equal the slopes from the right. That's probably a great way to state it there, because you are looking at a derivative, which are your slopes. The slopes aren't going to exist there. Now, at the same time, they've given you v prime at 20, and the biggest mistake that I've seen in years past, in the past couple of years that I've been doing this, right here people say, oh wait, there's a sharp point there, so that one's not going to exist either. That's not 20, that's 16. 20 is the y value, and they did that on purpose. They are just being total honey holes there. V prime at 20 does exist. V prime at 20, oh, I guess I need to put a 0 there. V prime at 20, notice it's talking about here. It's talking about the slope. It's down here. So it's not up there. And I get why everybody does that. And I even glanced at it the first time of this problem and did that. So V prime at 20 is going to exist. And notice we've got this ordered pair 16, 20, and then we have another ordered pair down here, 24, 0. So V prime at 20, if we're going to do our changing y's, we're going to have 0 minus 20 over changing x's, 24 minus 16. And so it looks like we're going to have negative 20 over 8, and you can stop there. Don't try to simplify that, because if you mess up simplifying, you're going to miss the problem. And then our unit of measure is going to be meters per second or meters per second squared, either way. And you know it's going to be squared because you're talking about the rate of a rate. Okay, our next question, a car traveling on a straight road from 0 to 24 seconds, the car's velocity. So automatically I'm going to stop there. I'm talking about the car's velocity, v at t, in meters per second is modeled by. So notice we have velocity. And the first thing whenever I'm glancing down through here, I see acceleration. So again, I go back to PVA. I'm at velocity. I'm asked about acceleration, so I know I need a derivative, which is going to talk about our slopes. All right, so let A at t be the car's acceleration. So now it wants us to write a piecewise defined function for A at t. Well, a lot of times people sit there and go, oh, piecewise, I don't remember. So let's review it. Piecewise just means it's divided up into different pieces. And here, since I'm asked for acceleration, I'm given velocity. This is just going to be a piecewise function of the slopes. So to write our piecewise function A at t, I know I've got a segment here, a segment here, and then a segment here. So I'm going to have 3 pieces to this. So one piece is going to be from 0 to 4, so I'm going to go ahead and put these. Now, as far as which ones are equal to, it doesn't matter. All right, and then the other, I'm going to say from 4 to 16. And then the last one is going to be 16 to 24. And so here, notice that I'm covering from each one of these values here. I'm covering from here to here, here to here, and then from here to here. Now, all I need to do is say, well, what is the slope from 0 to 4? What's the slope of that line segment? And notice we're here at 0, 0. So we had to rise 20 and run 4. So it's 20 over 4. And you can leave it just like that. You don't have to do anything else to it. Well, from 4 to 16, we're constant. We are horizontal, and that's going to have a slope of 0. And then 16 to 24, here we already have that slope. We found that earlier. That slope, I believe, was going to be negative 20 over 8. That's from the previous problem. It's the same exact value. And that happens quite a bit in your free response. So now we have our piecewise defined function. And let's see, that's all they asked for it. Okay, so part D asks for the average rate of change of V, average rate of change of V from this interval. So average rate of change again is your slope. Average rate of change. Now it's worded different, so it's not like the previous problems where it was talking about average acceleration so much. So for this one, the way it's worded, just average rate of change, we can go ahead and do our AROC with our velocity. So here, our average rate of change, we're going to say V at 20 minus V at 8 over 20 minus 8. So we're looking from 8 to 20. So we're looking from this interval here to this interval out here. That's what we're looking for. So let's see, what values are we going to get? So at 20, I believe we're at 10. At 20, we're here at 10. So we're going to have 10 minus, and at 8, we are at 20 over 12. And so that's enough. We can stop there, or if some people it's going to bother, but I would not go much further than this. Okay, now it says, does the mean value theorem guarantee a value of C? So mean value theorem, when you see this, we've only briefly talked about it. We've not spent a tremendous amount of time using it for a justification. All that mean value theorem says is our graph, is V at t differentiable over this interval? Is V at t differentiable over the interval, over the given interval? Well, if you're differentiable, then that means there's no sharp points. If you're looking at mean value theorem, you're looking for sharp points. So if I look for sharp points, then let's look at our graph. From 8 to 20, I've got a sharp point right here at 16. So if I have a sharp point, then the mean value theorem does not guarantee. So to answer that question, you would say no, because V prime at 16 does not exist, because again it has that sharp point there. And that would be it. That's all it needs you to say. Okay, for our next problem, 17a wants to know during what time does the squirrel change directions? Well, the squirrel is going to change directions at times t equals, let me get my pen to work, at times t equals 9 and 15. So t equals 9, t equals 15. And we know that because v at t, the velocity, has a sign change around these values. All right, so now let's move on to the next one. Write an expression for the squirrel's acceleration and velocity. So the acceleration should not be that bad because we're looking from 7 to 10. So let's look at our graph from 7 to 10. And this is the graph of velocity. So we have from 7 to 10. So looking at this, we're really looking at this one particular line segment here. The acceleration expression is going to be the slope, and then the actual equation of the line there is going to be your velocity. So here we can say, starting out, v at t equals, and then a at t. And I would go ahead and start with a at t because that's just your slope. So let's look, we've got 7, 20, and 10, negative 10. So if we do our slope formula, we're going to have negative 10 minus 20 over 10 minus 7. And so that's going to give me negative 30 over 3. So negative 10 is my acceleration. And now to come up with the equation for velocity, do your equation of your line. Y minus, and you choose one of them. It doesn't matter which one. I'll choose the top one, y minus 20, equals our slope, which is negative 10 times x minus 7. And to solve for y, which is really going to be your velocity, we're going to add 20 over. So I have negative 10 times x minus 7 plus 20. And there's our expression for our velocity. All right, our next question, we've got another particle motion problem. And we're told that we have a differentiable function v, so this is our graph of our velocity. And we are told that velocity is 0 at 0, 3, and 5. So here, where we've crossed the axis. And so the graph has horizontal tangents at, so I'm going to stop there. Horizontal tangents, so for the graph of v, this horizontal tangent here at these points at 1 and 4, then that tells me that a at t is 0. Our acceleration is 0 here, so that's important. And then the areas of the bounded region by the t-axis on the graph of v from these intervals, so from 0 to 3, I have an area of 8. From 3 to 5, I have an area of 3. And then 5 to 6, so we're going to drop a height down through here, and that's going to be 2. And so now at those times, we know at time t equals 0, the particle is at negative 2. So on answer choice C, on the interval from 2 to 3, is the speed of the particle increasing or decreasing? So again, right here, if we're talking about PVA, so again, P, V, and A, we're at velocity. We're given velocity from 2 to 3, so I'm going to highlight that region from 2 up here to 3. And we've got to go to acceleration. We're dropping down to acceleration. So again, moving down the chain, that is derivative, which is slope. So moving down that, we need to know, is speed increasing or decreasing? So I know speed, if it's increasing or decreasing, a at t and v at t, we need to look at their signs. So from 2 to 3, I know v at t, here, v at t, and we're really given our reason right here. V at t is negative. We know that because it's the graph of v at t and it's below the x-axis. I know that a at t, however, is positive because v at t is increasing. So therefore, speed is decreasing. As again, we have different signs. Now for part D, we have during what time intervals, if any, is the acceleration of the particle negative? Justify your answer. So let's go ahead and just justify it before we find those, because it tells us what we're looking for anyway. So I know a at t is negative when v at t is decreasing. So really this is just a matter of finding where is that function decreasing. So let's look to see over what intervals. Well, from 0 to 1, So I'm going to go ahead and say v at t is decreasing. And we've got from 0 to 1. And where else would this function be decreasing? It's going to be from 4 to 6. All right, moving on to the next. All right, so for part A, we've got to find the velocity for runner A and runner B. And I'm going to move these up here. I don't quite have enough room to write. So in A part, runner A, well, that's going to be kind of hard to find. We've got a line segment here, and we want to know after 2 seconds, but I can't really tell. It's somewhere between 6 and 7 there, and we don't need to write that. So what we can do is use our ordered pair. We know from 0 to 0, and then we've got 310. Our slope is going to be rise over run. So if we rise 10 and we run 3, so our slope here is going to be 10 over 3. And we can use the point, we can cheat. We can use 0, 0. And so my y-intercept would be 0. So my equation of my line here is y equals 10/3 x. And we'll need that 10/3 if they ask for acceleration anyway. So the velocity at time t equals 2 means we just need to plug in 2. So for runner A, it's going to be 10/3 times 2. And you can stop there. And I think we have to do units of measure. So that's going to be meters per second. And that's going to be it for that one. So that's going to be meters per second. Now for runner B, it's a little bit easier. They gave us an equation, so we're just going to plug in. And so V at 2 here is going to be 24 times 2 over 4 plus 3, and you can stop there. That's fine. And then our units of measure, again, that's going to be in meters per second. All right, now for part B, oh, look there. Now we need acceleration. So for our acceleration, not too bad at all. We already have it for runner A. So for part B, so for runner A, we've already found it. It's the slope, so it's 10/3. And this time it's meters per second squared. Now on our other runner, though, we're going to have to do the quotient rule to get that. So for runner B, let's go ahead and do our quotient rule. And like I said, I'm about out of room here. So I'm going to have the bottom. So I'm going to come down here and do my work. The bottom, so we have 2t plus 3 times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. And so from here, you can just plug in your 2 and be done with it. And you can even do some of this in your head. So if I plug in a 2, that's going to give me 4 plus 3. So 7 times 24, and I sure as heck wouldn't multiply that out. Minus, well, that's 48 times 2, and I, again, would not. And then that's all over. If I plug in a 2, that's 7 squared. This part right here, and don't box anything in, but that portion, that quotient there, is plenty to get full credit. Now, of course, you do need to attach your units, and me being out of room, it's kind of a pain to do. Let's see if I can scoot it over. So it's going to be meters per second squared. All right, and then for our last problem that we had on this packet, you're going to have which best represents the position of the particle s at t if the particle's velocity and acceleration are both positive. All right, so we know that v at t and we know a at t are both positive. And so we're asked for the position. So my goodness, let's go and examine some things here. So for A, if that's the position, velocity is positive, but acceleration is 0. So that's not going to work. All right, let's look at B. Notice this is concave down like a frown. That was the first thing I would look at, because since that's concave down, A at T is negative, so I know it can't be B. So let's look at C. C, well, we're concave up like a cup, so I know A at T is positive. My function is increasing, so I know V at T is also positive. So let's look at the rest of them. D, we're concave up, however, we're decreasing, and E, we're concave down and decreasing. So the best answer for that is answer choice C.